Welcome to this video on sequential circuits, a fundamental topic in digital electronics. We'll explore how these circuits introduce memory into digital logic. Sequential circuits are digital circuits with memory. Their final output depends on the present input and the circuit's previous state. This capability is achieved through a feedback loop, making them time-dependent. The key concept is that the output relies on the input plus the previous state. These circuits store information using internal storage and are time-dependent, meaning the same input can yield different outputs based on past events. Combinational circuits have no memory and depend only on the present input. Sequential circuits have memory, depend on past and present input, and use a feedback loop. Examples include flip-flops and registers. The memory concept is based on storing the previous output. The basic building block is a flip-flop, which can indefinitely maintain a single bit of data, a 1 or a 0, as long as it has power. Feedback is crucial. A portion of the output is fed back to the input, creating memory. Without this loop, the circuit would simply be a standard combinational circuit. It keeps data circulating until overwritten. The clock signal is the heartbeat of the circuit, dictating when events happen. It controls operation, ensuring memory elements only change value when instructed. It synchronizes millions of logic gates. The clock produces a square waveform. Events can be triggered by the rising edge, when the signal goes from 0 to 1, or the falling edge, when it drops from 1 to 0. Level-triggered circuits activate while the clock is steady at high, or LOW. Here is the sequential circuit block diagram. Notice the feedback loop, where the output is passed through memory elements before returning to the combinational logic. Sequential circuits are typically synchronous, strictly timed by a master clock signal, making them predictable and used in modern CPUs. Asynchronous circuits do not use a global clock, changing state instantly with input changes, but are harder to design. Sequential circuits are used in many real-life applications. Examples include digital clocks, counters for counting people, traffic light controllers that remember the previous light, and elevator buttons that store floor requests. In computing, sequential circuits are the basis for memory units like RAM, storing data for software. They form registers, which are ultra-fast CPU memory. They are the fundamental framework for digital systems like microprocessors and FPGAs. In summary, sequential circuits use memory via flip-flops, operate through feedback loops to maintain state, and synchronous circuits rely on clock control to decide when to update memory. Thank you for watching this video. Keep learning, keep growing.